multiplexers, I've received almost all of the questions that I've received regarding the C programming assignment that's due on Sunday at midnight. I received that question at midnight. It have been regarding multiplexers, so I've decided to dedicate a decent amount of this lecture to multiplexers and how they work. Also, for those of you for the C programming, I have posted, I sent an email out about this, but I wanted to reiterate. I posted a programming example where I've shown you precisely how I want it commented, precisely how I want the C files and the header files separated, and precisely how I want the report. So if you look through that sample report, you probably saw I have a number of little hints. Do this, don't do this, write this out, do it this way. So hopefully those will be able to answer all of your questions. And under that C programming assignment, I also posted the grading rubric I'm going to use. So you know precisely what I'm going to be looking for when I'm grading. So some of you probably looked at it. How many points am I taking off for improper commenting? What percentage? I'm guessing I just caught it. 15%. But you're right. So if you don't comment, you cannot get an A on the projects. Okay? That's by design, because you come in, as you notice, you start having big chunks of code, and then you have no idea where your error is because you're trying to figure out the flow and like what idiot wrote this code, and you realize, oh wait, I'm that idiot, right? So you don't want that to happen. So comment your code in real time. So the multiplexer, so the TGO is the definition, the drawing, and the truth table. And so there are two inputs, A and B, and a select line. And your output, I've defined it as F. So whenever S is 0, here's the simple way to notice this. Whenever S is 0, so 0, 0, 1, 1, notice how it matches A. And then when it's B, 1, 1, 1, 1, it will match B, right? Undo that. But you see what I'm saying here? So you have A and B, and the whole point of the select line is to be able to just make a decision on which one you want to pass. So I've provided a small snippet of C code here to show you how a multiplexer actually works. So I used a switch statement. In this case, the switch statement is select. It's a genuine switch statement. So I have input my select line as I've done here. Up here I have S, and then I have 0 and 1. So in case 0, I just want to return A. Case 1, I want to return B. So some people are coming in who are trying this and this very, very complicated code statements. I promise, students have come in, I promise to you I am trying to do these things that I'm doing to reduce the amount of time that you spend on coding. I promise I'm not trying to torture you. You may not feel that way, but I promise I'm trying. Okay. So, does anybody have any questions on this? All right. And so, here's how you can use 2-to-1 multiplexers to kind of build up to a 4-to-1 mux. All right, so there's multiple ways of doing this. You can either do this drawing where you're inverting all of the lines and then they're going into 3-input AND gates. So each AND gate is controlled by S0 and S1. So in a 4-to-1 mux, you're controlling, you have 2 select lines. Remember at 16, you're going to have 1, 2, and then you're going to have 3 and 4 over here. And so now you're having all these multiplexers here with 4 inputs, and then your 4 input here. So now you can see how, if you're building functions, if you have a 2-to-1 multiplexer, you can use 3 2-to-1 muxes to build a 4-to-1 mux. And then you can use 5 4-to-1 muxes to build a 16-to-1 mux. Yeah, that's typo. Because these are 4-to-1 multiplexers. So you have 4 4-to-1 multiplexers, and you have 4 outputs, and then you need 2 select lines to do another one, so you have 4 and 1 on the output there. So the whole goal is if I'm writing a 32-to-1 multiplexer, I could make this extremely complicated. I could do all this logic, or I can do code reuse. When you do code reuse, the goal is to significantly reduce the amount of time. So I can do 2-to-1 muxes, because remember in my problem statement I said you have to use 2-to-1 muxes. What I didn't say is you can build functions that use 2-to-1 muxes, right? There are shortcuts. I promise if you use creative shortcuts, I will reward you, not punish you. So it's like, all right, well, I built a 4-to-1 mux using 2-to-1 muxes. Okay, cool. It still uses 2-to-1 muxes. So now I use 16-to-1 muxes, which is using 4-to-1 muxes, which are still using 2-to-1 muxes. Therefore, they still meet my problem statement, right? You have an opportunity to be creative. Use it. So then if I was building a 32-to-1 mux, which I believe is your problem that's due on Sunday, how would I use what we've done here to continue doing that? 2 16-to-1 muxes, so now I've got 2 outputs, and then one more 2-to-1. Bingo, very good. You guys might be engineers yet. So does this make sense? So this is kind of the idea of what I want you to do. So I wanted to combine some concepts here. So I brought back our good old Carnot maps. And so how do we actually design a 2-to-1 mux? What's the actual physical implementation? So using a Carnot map to design a 2-to-1 multiplexer, draw the gate level design. So here, ignore this stuff about literal cost and everything, but I have a select line, A to B, and so we have A and B, we've done our gray coding. So we have 0, 0, 0, 1, 1, 1, 1, and 0. So last section we learned some of the real benefits of speed versus performance versus power consumption of gray coding. And then 0 and 1 for select lines. So here, I know I'm going to get the question. I've deliberately left it out, but because I'm going to allude to it later. So here, 1, it's just 1 and 1. And 0, you're 1, 1, and 1, 0, right? So here I've reduced it. I've taken the logic S, A, and B, or S bar, A, B, or S bar, A, B bar, which reduces down to just S bar, A. And then again, S, A bar, B, or S, A, B, which just reduces down to SB. So now your logic function for your multiplexer is S naught A or SB, which then comes to this circuit here. So then we have our S, we invert it, and it's ANDed with A. S becomes B here, so this is an AND here. And then we have an OR function that takes both. So you can design a 2-to-1 mux in multiple ways. You can design a mux using a switch statement, or if you're more comfortable designing them this way, you can use NOT gate, 2 AND gates, and an OR gate. Either is sufficient, both will work, both will give you the same results. So before we move on, what is the one issue with this K-map that I've done? Yes, race condition. I didn't do this, right? So here it's not a sequential element, so it's not going to be that much of a deal, but big deal. However, the S has to go through this inverter first, right? Whereas this doesn't have to go through an inverter, so there's a little bit of a lag. So you're going to have a moment here where the result from SB is going to beat the result from AS bar. So that's where we can modify our result. So I left a little space here, or did I not? Oh, I thought I had. Okay, so we can just do it here. So let's work through this. So now we have our third condition, where this is just AB, right? Every time. So it's S bar, A, or SB, or AB. It's not going to change the logic, but we're going to be gaining additional overhead. So now you're adding here. Now if you want to add a 2 to 1, or you put that out there, and now clear all, please. Thank you. Go away. Go away. Yep. So now that's where you have your trade-off between size and race issues. Okay, so does anybody have any questions about that before we move on? So demultiplexers. So I have multiplexer, I have 4 to 1 multiplexers, but here, this is a 1 to 4 demultiplexer. So a demultiplexer is a single input signal. In this drawing, this is F. So you have some sort of single input signal, and now we're using 2 select signals to determine the output that we're going to select here. So what's going to happen is we have 1 input signal and 2 input signals here, A and B, and you can either have 0, 0, 0, 1, 1, 0, or 1, 1. And if you look at, I'm going to read the definition. I'm going to zoom in on this drawing. A demultiplexer is a single input and selecting one of the many data output lines which is connected to the single input. So here's what that means. Zoom in on the diagram. You can now see A, B, and F a little more clearly. So here's what's happening. We have this one F input line which goes to all 4 3-input AND gates, right? So that's our single input line. And then we have these 2 signals. So A is inverted, and so this, this A goes here, so here it's inverted, and so it goes here, so it's 0, 0, right? And if it's 1, it goes here and here. So you can see it's 0, 1, 0, 1. And then for B, we have it's inverted, comes here, here. So for B, it's 0, 0. And then for, choose brown. And for B, when it's not inverted, it goes here and here. So it becomes 1 and 1. And so what happens is, if F is 0, it doesn't matter. It's going to put 0 on all the outputs, right? So if I don't want to select any of the outputs, it's 0. But when it's F is 1, that means the truth table becomes so now but since you've got all of these inverted, the value when A is 1 and B is 0, that means this value is inverted. So we're going to go here. And 1 is not inverted. So we can go here. And so it's going to go there, and therefore we choose that value, right? So the whole idea is you have to meet the conditions of the specific AND gates in order to be able to select your demultiplexer output. So here's where this can be useful. So when you have a coaxial cable, right? Coaxial cable delivers your cable to your computer. And so you have a number of signals that come along with it. And one of these signals, they all go in a little stream, one stream, along with a select line. So what's happening is every second, you're not only getting every pixel of your screen, but it's also, once you select, you can get all the pixels from the different channel, right? So I want a specific channel. So at the cable user end, they're going to multiplex that signal into 1 and then pass the select lines across. And then when you, the user, want to pick HBO as opposed to ESPN, you just change your select lines, and now you have the different value, and as a result, you're going to get the specific channel. And so this is what's known as a 1 to 4 demultiplexer. So let me go back a little more. So I'm going to expect you to do a 1 to 8 demultiplexer on your coding projects. And so another thing I noticed when I was helping students, and I wanted to include this logic synthesis here regarding multiplexers, is that some students noticed when they were looking online to kind of get some assistance on the adder subtractor, that when they saw the adder subtractor was a multiplexer with a uniquely kind of tied select line. And what happens is you can actually use multiplexers to design XOR gates. And so this is an example of it here. So what we've done here is the of your XOR 0001, 1011, and you have this output, right? So you do a very simple K-map. F equals A not B. A equals, or A B bar. So this is A bar B or A B bar. So the simple way to use a multiplexer to do this is just to have a B input, that value and its inversion, put into a mux, and use A as the select line, and now you have your output. And so this is what a lot of people were seeing when they were researching online. They're like, well, what's that? Why are they using this multiplexer? They're just doing that as a different way of, that's logically equivalent to an XOR gate. And so what we're going to do in the next example is we're going to design A XOR B XOR C in using 2-to-1 multiplexers. So here's what we have. We have our logic truth table. Let me zoom in a little more so that way it's clear to everybody in the class. All right, so what you can do is you can break this in half, and you can see that this is our XOR, right? If we have this for B and C, it's our normal XOR, 0, 1, 1, 0. But if you look at the second half, you see this is 1, 0, 0, 1. So that's actually the inverse of the XOR, right? Of the original XOR. So this is 0, 1, 1, 0. And then here it's 1, 0, 0, 1. So it's just these values inverted. So what you can do is you can use B or C initially, like we did before, with our multiplexer here. So then we get our B or C result, which is equal to that. And so if A is 0, then we're just passing this value, right? But if A is 1, it's inverted. So what we've done is we just invert the signal again here. So the way this signal looks is you got C value and it's inverted. And here we use the B input as our select line for the first 2-to-1 multiplexer. And this brings B XOR C on the output. So when it's 0, we just want the value to pass through again, right? But when it's 1, we want the value to invert. And then we use A as our select line. So that's how you can use these primitive blocks to be able to kind of build other logic gates. Does this make sense? Our multiplexer is starting to make more sense. So here's another reason why multiplexers are really useful. We're going to talk about this concept called Shannon's expansion. Okay. So any Boolean function, we call this W1 through Wn. So these are our inputs, logic inputs. So when we have a 3-input XOR, W1 can be A, W2 can be B, W3 can be C, right? This function can be written in the form W1 through Wn is equal to function 0, comma, W2 through Wn, or function 1, W2 through Wn. So what that means is you can take any variable in that function and reduce the remainder of the function to, if that variable is 0, the result is going to be this function. And if the result is 1, it's going to be this other function. So for example, in that last problem we did, we saw that if we call this A, B, and C equals, so when A was 0, this became B XOR C, right? Or f of 1, B XOR C not. So when we do the Shannon expansion about variable A, we get two very unique different functions. Now, why do you think Shannon expansion, what logic structure have we been learning all day that can make Shannon expansion very simple to implement? Multiplexers. Okay, good. You guys are starting to get it. I like that. So Shannon expansion is actually something that's highly used in hardware security. Use a lot of Shannon expansion to be able to, do the advanced encryption standards, to be able to design Xboxes, to be able to encrypt and decrypt signals. So you combine Shannon expansion with a lot of your multiplexing and demultiplexing and logic gates, and so you have an input key, and then you do round values where you're going to be adding it, bit shifting, and then you do it 8 times for AES. A lot of Shannon expansion in there. So Shannon expansion is particularly, when not to get too much into quantum computing, but XOR gates are the fundamental logic structure for quantum computing, such as, for example, in CMOS, it's the AND gate. So being able to combine multiplexers and XOR gates, you can do a lot of encryption, hardware security, that kind of stuff. So Shannon was one of the he was one of the guys who was really fundamental into security algorithms, and so a lot of that's just based off of multiplexers. So the TA for this course, Mr. George Humphrey, I think many of you know who he is. When we did this course last year and I discussed this, he got really excited about hardware security. Now he's doing research with me. So for whatever he'll tell you this story if you talk to him about it. He was considering dropping out of double E, saw Shannon expansion, like, that's what I want to do for the rest of my life. Yes. So I don't know if that's inspired any of you like that, but you never know what you'll come across in the course. And no. Anyway, so getting back to why I'm teaching it to you guys, you can use these logic circuits to reduce overhead. So here we have a majority voter that we're going to be using Shannon expansion about the variable A, which means we're going to figure out two functions, and A is going to be our multiplexer. So we've broken this down. F of A, B, or C, just like the definition, is AB or AC or BC, because so a majority voter is, you've got to put output of 1 when at least 2 inputs are 1. So here you have a bunch of zeros until you get to B or C is 1, and then you have a 1 on the output. And then once you have 2 or more, so it's the majority of inputs. So then the next step is we're going to do Shannon expansion about A, which means we cut this guy in half. And we see our function outputs. Now, you can do one of two things. Here, it's pretty intuitive what the functions are. If it's not intuitive, you can do a K-map. Or if you remember, how many you guys did you guys do QM reduction in digital systems? No. Klein-Mikulski?
Yeah, we did a little bit.
Okay, you guys knew it gave me a heart attack. I'm like, oh, okay, well, I know what we're doing on next Tuesday. Yeah, so you could do QM reduction, you could do K-maps, you can do anything to figure out this. But here it's pretty intuitive. So to save you time and energy, This is just B and C, right? And here, when it's 1, it's B or C. So then what I can do is I can just do B and C there when it's 0, B or C when it's 1, and then just put it into a mux. And the reason why this helps you is because if you didn't have that, you would have to do this as a K-map, the whole circuit. So now you've turned it into 2 smaller K-maps, and in this case, you've actually made it easier on yourself. And so I'm going to show you an example of 5.4, a more complicated example. So here, given the following function, so I have A naught, C naught, or, are you able to see that? I can figure out other ways to make that clear. A naught, C naught, or AB or AC. Design the circuit using a 2-to-1 multiplexer and any other necessary gates. Use a Carnot map to derive the input functions for each of the 2 inputs to the multiplexers for each variable. You may only use AND, NAND, OR, NOR, and invert gates as the inputs to the multiplexer for your final solution. So here, this is where I'm concerned, so I want to make sure you guys can see the circuit. So the first thing, here's the truth table. I'll zoom on it a little more before we get into the K-maps. A little more. All right, so A naught, C naught, or AB or AC. Let me make this red so it's even. So 0, 0, 0 is 1, 0, 0, 1 is 0, 0, 1, 0, A naught C, so there you go, you got 1, 0, 1, 1 is A naught, so that doesn't mean any condition, so it's 0, 1, 0, 0 is 0, 1, 1 meets AC, so it's a 1, 1, 1, 0 meets B, so it's a 1, and then 1, 1, 1 also meets AB and AC, so it's a 1. So it's 1, 0, 1, 0, 0, 1, 1, 1. So on each of these, I have done an example of a K-map about each variable. So here I've asked you to derive the input for each of the 2 inputs to the multiplexer for each variable. So what that means is I wanted you to do the K-map for A, B, and C. So in this case, we're doing the Shannon expansion about A. The second one, we're doing the Shannon expansion about B. And here we're doing the third Shannon expansion about C. About A, we have our blocks here. We reduce it down to when A is 0, it's A naught, and it's just C naught. When F is 1, when A is 1, it becomes B or C. When we're doing the Shannon expansion about B, when it's 0, we can see it's 0, 0, or 1, 1. So it becomes B naught, A naught, C naught, or AC. And then for 1, it's A or C naught, so it's 0, 0, 1, 1, 1, 0. Right? And then I'll scroll up so those of you in the back can see the expansion about C. And then here, so again, we've kind of done the same thing. It ends up just being virtually the same thing as the A one. So for C naught, it's A naught or B, or for C, when it's 1, it's going to be just A. So here, the next thing I've drawn out all 3 circuits, and you can make a comparison as to which circuit you think is best. So by drawing out each of these circuits, let me zoom in on A first. So this is the A circuit. So here it's just C naught goes into 0. For 1 it's B or C, right? When it's about C, and I'm doing it in this order for a reason, you'll see when I get to B, it's A naught. When it's 1, it's just A. When it's 0, it's A naught or B. And then when we go to B, when it's about B, this is the size of the circuit. So you can see how it kind of gains a size. So the reason I've included this problem is to show that even though you might be doing the same approach, you want to check all possible solutions. So you can expect a problem similar to this on the exam. Ignore all the stuff about the literals and the gate costs. But to get into that just a tad, which of these 3 circuits do you think would be best? If you are, I am the boss man, I'm the guy from Dilbert with the hair sticking up like this, and you're the engineer, I'm asking which of these 3 circuits, which one of these would you use? First one, so I hear a lot of A. Why A?
Because the input from the inverter and the gate will reach the multiplexer at the same time.
Approximately, yes.
Actually, see, that'd be better if you have fewer gates.
Well, I mean, these are both OR gates, and then you have not and not here.
But if like A goes to the multiplexer first, then would that be like the shortest time?
Right, but that's the case they're making is that you have a delay here, so you don't have as much of a race condition. So that's a trade-off. If you make the timing short enough, then yes, it would get there faster. But what they're trying to do is they're trying to reduce the amount of time that it takes. Ultimately, you would want to design your timing to be able to allow it to get there, and then you would have latches on the. When we get to pipelining, you'll see that we have latches at the end of each stage, and so once you get to your edge-triggered flip-flop, then it'll pass the value through. So that should negate all of these little errors that you have. But if you're thinking about it from the perspective of race conditions, this reduces enough the probability of an error. And you definitely don't want B, right? That's nasty. Okay, so the last combinational thing I wanted to go over with you guys before we go back into C to MIPS coding is this concept of a decoder. It dawned on me, especially with designing a MIPS data path, you absolutely should know what a decoder is, so I'm reintroducing it here. A decoder is a digital circuit that performs the conversion of an n-bit input code to an m-bit output code. So that n is less than n is less than or equal to m, and m is less than or equal to 2 to the n. And so, for example, if the number of inputs is 2, it should be less than or equal to m, which should be less than or equal to 2 to the 2. So therefore, at most you want a 2 to 4 decoder, or 3 to 8, 4 to 16, 5 to 32, and so on. And for example, just a simple 1 to 2 decoder, if A is 0, here's what's going to happen. When A is 0, it's going to get inverted, and this output's going to be 1, and then this output's going to be 0. So you're going to get 0, 1. And then when A becomes 1, this output is going to become inverted, so this is going to become 0 and 1. So the values are the opposite. So you're actually just using this 1-bit value to decode it. And the same thing with a 2 to 4 decoder. If 0, A is going to be 0 or here, and if it's 1, it will go here or here. So it's kind of the same concept we were using earlier, except in using select lines in 1 bit, we're actually using the lines here to just decode. And so then you'll get these data outputs. This is D0, D1, D2, and D3. This output is true if A naught, A1 naught, A0 naught. So this is A0 and A1 for our inputs. So this is A1 naught and A0 naught. So this will be, so you can come up with a truth table here, which I've already included. So it's 0, 0, right? So you can see that there will be only one line that's 1, correct? What do we call this in last section?
One hot encoding.
Correct, it's one hot encoding. So now I'm showing you how to take in a, so let's combine some concepts. So let's go down there and then let's combine some concepts. Sorry, I want one more thing. So you have an enable line here. So yeah, you can actually make it more complicated. You say, I don't want it to decode unless I've enabled it. So I can add this set of AND gates here. And if it's 0, it doesn't matter. I'll put 0 on all the outputs. But if it's 1, then it will choose an output, right? Okay, so 3 to 8 decoders and 3 to 8 decoders. And again, what we've done here is we've kind of used logic structures, AND gates, NOR gates. So you have your third input, and what happens a lot here is you're taking in your AND gate results. I'm sorry, let me get rid of this to make it clear. So here, what you're doing is you're taking your AND gate results, and each of them is going to go to 2 because it's binary. And then you've taken in yet another signal. If you wanted to make it 16, you would add a fourth one. If you want to make it 32, you would add a fifth one and come up with the logic like that. And then again, we have our one hot encoding. So before I scroll down, now I want to combine some concepts. So how many, we talked about memory a little bit, it specifically registers about how we want to have a select line, right? To be able to select which value we want to write to. So how many registers do we have in MIPS? We have 32 registers in MIPS, right? And when we selected which value we wanted to do, what do? We iterated through the 32-bit value, found the one that was selected using one hot encoding, and that became the write line or the read line. So now we have 32 inputs, right? To get to our registers. Then we talked about RS, RT, and RD. Those are our addresses, right? How many bits in the instruction are dedicated to which specific register we want to use? 5, right? RS is 5 bits, RT is 5 bits, RD is 5 bits, right? So now I have a 5-bit input telling me what the address is. And I need to select it using some 32-bit output. So I need some sort of magical thing that gets me from here to here. Decoder, right? So I need some sort of 5 to 32 decoder. So this could be RS, and then you include another one for RT, and then you include another one for RD, right? So this would be, your result would be read reg 1, read reg 2, and then read data. So that's where this comes into play. So you take your instruction from the instruction memory, you get those 5 bits, you have a 5 to 32 decoder, and then you get the resulting value that you want on the output. And then, so for programming assignments, I want you for practice to do 1 to 2 decoder, 2 to 4, 3 to 8, and then 5 to 32. That should be 5.5, not 5.6. I'll fix it. So as you can probably see from the combining concepts, that the problems are starting to fit together a little bit. So the whole goal is you should be able, now once you finish this project, you're going to be getting from, LSI. Now you're getting to MSI, and then you're getting to MSI to LSI here, and then once you start putting the pieces together, that's when you become VLSI, and then you've created an advanced digital system. So you're getting close. So it's 10-7, like that. So does anybody have any questions on this? If I had one last thing, this is a common thing, people seem to be overthinking this on the coding projects. One of my problems was the 64 to 32 mux, right? So let's solve it in class together. There's multiple ways of doing this simply. So what is the 64 to 32 mux actually doing?
It's taking 32 bits and selecting them.
Yeah, both of you are saying the same thing. So I have two 32-bit values. One of them we'll define as A, which is 32 bits, and one of them is 32 in B, right? And they both go into this multiplexer, and I've indicated I only want one select line. So it's not like a 64 to 1 where I require 6. I only want one select line. So, and I have some F on the output. So how would I code this? What would your approach to this be? What was my design constraint on the problem? Well, the for loop was not what I said in the problem. What's the design? I have to use 2 to 1 multiplexers, right? And so then, now you guys have solved the problem. That wasn't my design constraint, that was the solution. So what I want you to do is I want you to go for, I'll write it on the screen here, because we're running it. So for I equals 0, I is less than bits, I plus plus. And then you can have result of I, so you have some sort of allocated memory. Result of I is equal to mux A of I, comma B of I, right? So now because what you're physically doing is you actually have 32 2 to 1 multiplexers there in the logic structure. So I'm having you actually code up how it's being done. But what I don't want you to do is write mux, 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 mux. Use the for loop to save yourself time. And then you will return the function to 32 and you've properly done it. So the reason why I'm having you do the 64 to 32 mux is, you know how I said in R-type instructions that RD is the destination register for R-type instructions? But for I-type instructions, which one was it? Somebody said it. So RS is never, but RD is for R-type, and what did I say it was for I-type? RT. So you got to make some sort of decision, right? So I have a 64-bit destination, a 32-bit destination RD, 32 potential RT, and I have to decide between those, right? So I'm going to use a control signal. We're going to learn about those a little later, called register destination. You put that in, you use your 64 to 32 mux, which you've designed in coding assignment 1. You produce your output. You send that to your registers. You use your 5 to 32 decoder to determine which one you want. Boom. All right. Okay, so now I want to show you a really neat trick that you can use with decoders before we continue to move on. So I've included 2 problems here, 5.5 and 5.6. So I've given you 3 min terms using a 3 to 8 decoder and 2 input OR gates only. Design a logic circuit that implements the following function. So F, A, B, and C. The min terms are 2, 4, and 5. So you could drop a fancy K-map, spend all this time and energy, or I just have my 3 to 8 decoder, and then I just have my outputs 2, my outputs 4, my outputs 5, or OR gate function. So this is where you can start using your designs to reduce overhead design complexity. So what's the drawback to this approach? I'm sorry?
It probably uses more gates than necessary.
Probably uses more gates than necessary. So when you get into FPGA, specifically in 386, you're going to be using these anyway because there are primitive blocks, lookup tables, decoders, and so you can use this to significantly reduce your overhead. Sometimes synthesis time is what's important. This will reduce synthesis time. But when you're dealing with synthesis time, sometimes you're reliant on the synthesis tool, and as a result, you get bloat. So there's pros and cons to all this stuff. So I've drawn a second example where the min terms is 5 inputs, and I'm still only using 3 to 8 decoders, and I'm still using 2 and ORs only. But my min terms in 5.6 are 1, 6, 12, 17, 27, and 31. So this is where it starts getting more complicated. So what I've done here is I've broken my truth table. Since I'm only allowed to use 3 to 8 decoders, I have the least significant 3 bits going to one 3 to 8 decoder. And then I have the most significant bits, AB, going to the first 2 bits of another 3 to 8 decoder, and the other input is held at 0. So now what happens is 1, 3, 4, 6, and 7. I see which ones here. 1, 6, 4, 1, 3, and 7, right? Are the bottom values 1, 6, 4, 1, 3, and 7. So I don't need the other values. So I will get those outputs. And here I see 0, 1, 2, and 3. So then I just use and OR gates to determine which ones I want. So I'm going to scroll up for those in the back. 3 to 8 decoder. I have 1 either goes here when this output is 0, or 1 comes down here when the output is 1, right? I'm sorry, when it's 2. And then you can build this whole circuit here based off of 3 to 8 decoders. So as these circuits become larger and larger and larger, and when you instead of dealing with 4 or 5 inputs like you would on an exam, when you're dealing with 32 inputs or 64 inputs, you want to try to reduce your design overhead. And while QM reduction gives you the optimal solution, it does take a lot of time. So a lot of synthesis tools will use heuristics. Does anybody here know what a heuristic is? Yeah. Anybody else? A heuristic is what's known as an approximation algorithm. It will give you an adequate solution which is close to the best. You take an algorithms course, there's a whole field of study known as approximation algorithms because there are these issues dealing with something called NP completeness. So there are algorithms that can be completed in polynomial time. There's some where we're not sure if they can or can't be, and trying to figure out some that can't be done efficiently using a computer. So you try to get really close to the right solution. That's what's known as a heuristic. So you can start using these to kind of get up to a heuristic. So the trade-off is that you're using these 3 to 8 decoders, this design becomes less complicated, especially when you get to larger and larger circuits. Right, so that's the full solution right there. Okay. So does anybody have any questions about this? The multiplexers make a lot more sense. Decoders, demultiplexers. All right, so for the last 20 minutes of lecture, I kind of want to dive back into this concept of register instructions. So on Blackboard, I've included so what's known as the MIPS green sheet. For those of you who have the textbook, it's that first page where it's that green flap. And on there it has all of the instructions that can be used in MIPS, all the instruction formats, If you've looked at it, you've probably actually seen the IEEE 754 format on there and how it's used in MIPS. Any general thing that you would need is on there. So when you start building your data path, it's going to become intensely useful. So I've included this example of an AND instruction where this is the operation. Now, we haven't learned Verilog, but this is the operation in Verilog. If register RD is equal to register RS plus register RT. And then over here, I have this funky thing, opcode, funct, and hex. So what are these 6 portions of the instruction, of an R-type instruction? Opcode's one of them. Funct's on the other end. So what are my other 4? RD's one of them.
RT and RS.
And I'm missing one. Shift amount, right? 5-bit shift amount. And why? Now that you guys know what you know, why is shift amount 5 bits? 32 bits. And so if I have a 5-bit shift amount and you're coding, what are you using for shift amount? What's the concept? What's my constraint in the problem? You're doing one hot encoding, okay? So what do you need to do to be able to get from your one hot encoding to the instruction? I got my shift amount. Now I have my one hot encoding, right? So, but here, what this is telling us is we have our 6-bit opcode and our 6-bit function. Remember from section 3, you receive this funct value into the ALU control, and it gives you that 4 ALU bit output, which then goes to the arithmetic logic unit. So remember we have 16 potential functions we have there. So here's what's happening. What this means is that the first 6 bits of the instruction are 0. That's your opcode. The last 6 bits of the instruction are 1, 0, and then 4 zeros. This corresponds to 2, 0, and hex. And then, for an R-type instruction for add, the shift amount is going to be 0 because you're not shifting. And then the rest of it just corresponds to RS, RT, and RD. Now typically, those values correspond to, if you remember all the way back, this is page 10, so I can go to page 1. If you remember this table here, those values just correspond to this number. So if I'm using save temporaries, I start with 16, so that's a 5-bit value. So that means it's just 1, 0, 0, 0, 0. That's why like S3 is just 16 plus 3 is 19, so that becomes 1, 0, 0, 1, 1. So going back to where we were before, I just described all the things. So if RS and RT in the same register, that's fine because we just have 2 values in the same instruction. I probably could have deleted this paragraph because I've drilled dual read, single write SRAM into you guys pretty well, right? So the reason you need to do that is because of dual read, single write SRAM, but we have accomplished that in previous sections. So example 5.7. So this is now we're taking assembly code, and we're going to take C code, and we're going to go to assembly code, and then we're going to go to machine code. So now we're kind of taking this concept where we've been building this underlying hardware that you can use but can't manipulate the organization. And now we're doing this compiler-driven encoding of the micro engine to get it down there to have it flow through. And now we're learning our architecture. So in this problem, translate the following C code into the MIPS register transfer language, assembly code, and then, I see it. Register transfer language, which is VHDL, and then the MIPS assembly language, and then the machine code, where A is stored in S0, B is stored in S1, and C is stored in S2, and D is S6. So those are our saved temporary registers. And our C code is a simple A equals B plus C plus D. So our constraint in MIPS is that an R-type instruction can take two variables, perform an operation, and store it in the third register, correct? That's the definition of R-type instruction. But here we're trying to add three numbers, three integers in this case. So what we need to do is we have 8 saved temporaries, right? But then we have 16 other temporary registers that we don't allocate to variables. That means you don't want to overwrite this value A. You have to do what the compiler tells you to do, right? So, or what the coder tells you to do. So in this case, a common student mistake is to add B or C and put it in A, and then to add A and D and put it to A again. But why is that wrong? Okay. At no point does the coder say A equals B plus C. And especially when you start dealing with parallel processing, you start having intermediate instructions, and you have to maintain what's known as cache coherency, which we'll learn about in section 7. That becomes extremely important. So here, this is our simple values, where we've done the same thing. We have S1 and S2, that's B and C. This is from our MIPS green sheet. Actually, I will put that in green so you know to look in the MIPS green sheet. So that's MIPS green sheet here. So these are two add instructions. So this is RS1 plus RS2. We have selected one of our temporary registers, T0. And then what we're going to do in the second instruction is take T0 plus S6 and store it in S0. That should be S6. My apologies. These should be. This is backwards. This is S. D is X6, and then A. No, this is right. Sorry. Correct. I had put the correct answer. I overthought it. S0 is A. SD is 6. And D is S6. So T0 plus S6 is put into A, which is register S0. Question: why is this wrong? Common student mistake. Why is that wrong? S6 plus RT0. So I put them backwards.
It's not in correct order.
Correct. Order of operations is extremely important. You must do it the way the coder has told you. Compiler-driven encoding of the micro engine means the compiler drives it. Now if you want to take grad computer architecture, which is offered by computer science someday, you can learn a lot about out-of-order operations, loop unrolling, things like that. But for this course, I will expect you to do proper order of operation. So we have now done our register transfer language, that's this, and we have now translated into the machine code. So in MIPS, if you look at the assembly language of RS, RT, and RD, so the order of operations here in the assembly language is this, right? I'm passing notes. Is this kindergarten? Please put that away if it has nothing to do with class. Thank you. All right, so now let's convert this to machine code. So here the assembly language, we're adding these two values and putting it here. So now we know our opcode is RS, RT, and RD. So our order of operations is this is going to be the first one we add. So this would be B plus C, and that's going to be put into T0. And then our next one would be T0 plus D, and RD is going to be A. So let's do this conversion. We know from the MIPS screen sheet that our opcode for add is 6 zeros, that the shift amount is going to be 0 since we're not shifting at all. and that our funct is 20 hex, so that becomes 2, and that's 4 zeros. So that becomes, so we've now solved half the problem right off the bat. And then we go down here. So we know that S1 is going to be 16 plus 1. So that's going to be 17. So that corresponds to this one. We know that S2 that was C, so that's S2. So that's 16 plus 2, right? That corresponds to this guy. And we have temporary 0, which is 8. So that's 0, 1, 0, 0, 0, which corresponds to this one. So here we've taken our opcode 0. We've taken our shift amount here. And we've taken our funct 2x hex, which is this, and put it here. And our result, I'll scroll up a little bit for those in the back. We have our opcode S1 and S2. They are added and put in the destination register T0. We do not shift. And then we use 20 hex to represent the function for the first instruction. Now, for the second instruction, again, it's an add, so it's 0, 0. Remember, we are adding T0, that's going to be 8, plus S6, so that's 16 plus 8, which is 24. So this becomes 0, 1, 0, 0, 0. This becomes plus 8, and plus 6 is 0, 1, 1, 0. And the destination register is S0, right? That's this guy. It's equal to 1, 0, 0, 0, 0. So you can see here, let me put this in red. That goes there. This one is 24. That one goes there. The destination register goes here. Again, we don't have a shift amount, and still 20 hex because we are still adding. Does anybody have any questions about that? No, I just threw a lot at you. Maybe I have this little paragraph that we've already talked about my order of operations. So we'll do one more problem, then we'll dismiss you guys. We'll do order of operations. We'll do example 5.8, and then you'll be dismissed. And I'll email you guys the homework. Should be, I'll get all the proper TGOs. So for 5.8, I have this funky little problem here where I have G plus H minus I plus J. And so be mindful of order of operations again. What do you have to do here? Before we even deal with code, what's the proper order of operations?
G plus H.
Mm-hmm. I plus J. And then subtract. Yeah. Mm-hmm. And remember, in MIPS you can only do 2 at a time. So you have to do them in that kind of order.
You're going to dance?
MIPS. Dance to hang up. Now I can see what they cast at. All right, so everyone will turn their cell phones off now, won't they? Yeah. Mission accomplished. All right, so that might have hurt me. All right, so same thing. We have S0 in G, S1 in H. So the first thing we've done is added them and put them into T0. The next thing we do is have I and J. I is in S2, J is in S3. So you have S2 and S3, and we've done T1. That's our another temporary. And then we have a subtract function value where it's T0 and T1, but T0 minus T1 are put into S4. So if you go in the MIP screen sheet, you will see that that is our Verilog code. So that's the register transfer language. And so we'll break this down into machine code. For R-type instructions for subtraction, all R-type instructions start with 0. So if we go to the MIP screen sheet, we would see that subtract starts with 0, 0. When we go to the MIP screen sheet, we're going to see that it's 2 hex for subtraction. So that means it's going to be 1 0 0 0 1 0. So that's going to be our function. So that's going to be the last 6 bits of a subtraction instruction. So for add, it's still just 0 0, no shifting, to 0 hex. And see this 1 bit that's different? That's what you're going to use to tell the difference between when you have your, your carry, your initial carry in, and your adder subtractor. So putting this all together, this is S0, that's S1. We add those and we put them in 8, which is T0. Next, we're going to add, because we can see here is add. This becomes S2 plus S3, goes into T1. Because we starts with 8, we've added 1, so that's 9. And so here, we've used this function to indicate subtract. Our shift amount is 0, 0, 0, 0, 0. So we have T0 minus T1, and we put it into S4, just like we've done here. S4 is 16 plus 4, so that's 20. So that's that value there. And so that, I think I've covered all the common student mistakes. I'll upload the video and send it out. Please feel free to shoot me any emails regarding assistance with the coding project. Is due Sunday at midnight. Under C programming assignments, you can find the grading rubric, a programming example that I've submitted to show you exactly how I want it, and that's where you'll also find the submission link. I only need 1 submission per group. In fact, if it'll make it a lot easier for me to grade. Because I'll go there and I'll see a second one. I go, oh, hey, just graded that one. Hey, it's a momentary inconvenience, but, happy grader equals happy grades, right? You're dismissed.